So in this lesson, we are going to continue solving differential equations. We're going to expand the type of differential equations that we're looking at to ones that are not explicitly solved for y equals. So we'll talk about how we would want to solve these types of differential equations, and then we will also look at one of the most common applications of differential equations, which is the law of exponential growth. So just as a quick recap from the previous lesson, recall that a differential equation is an equation that contains at least one derivative. So if we have something like dy dx equals x cubed minus 2x plus 7, when we're asked to find the solution or to solve the differential equation, we want to find the original function whose derivative is equal to this. So we would just say, all right, so we know that a possible function that would have this as its derivative would be something to the fourth power. I would have to have a 1/4 out front to compensate to get that to be x cubed. So minus x squared plus 7x, and then there could be a constant there that we aren't able to determine, so we have to write that as a plus c. So we do consider this the general. So this is the type of differential equation that we've been working with, and it's solved explicitly for dy dx equals, this whole side of the equation here is written in terms of our independent variable x. So what we're going to be looking at today is we'll probably still continue to look at some of these, but we'll also have some written implicitly where the x and the y are mixed together, and we'll talk about how we can algebraically deal with the technique for solving these. All right, so I had mentioned that some of these are going to be written implicitly. So implicitly means that their x's and y's are going to be mixed together. In order to use any of the integration or antiderivative techniques that we've discussed, you need to be able to separate the variables. You need to have the x's together and the y's together before you're able to take the antiderivative. Something to note is that when we separate the variables, we do need to keep the proper form for integrating that follows along with the definition of an integral. On one side of the equation, we need to have a function or an expression written in terms of y as a product with dy. Going along with the definition of an integral, this proper form comes from taking the area under the curve using an infinite number of rectangles where the function is representing the height of those rectangles and dy is representing the width. Similarly, this side needs to keep the same form. So in order to be able to integrate it, we need to have it as a product of a function or expression with dx or dy. So keeping that in mind, you are going to be using a variety of algebra techniques that you've picked up throughout your high school career. Just be careful not to invent new ones. So I know that maybe sounds kind of silly, but make sure that you're following rules and that you're keeping the integrals in this form before you take the antiderivative. All right, so if I have dy dx equals 2x over y, notice dy is on top here, so we want to keep y on this side of the equation. So to get y on this side, I would multiply both sides by y, so I end up with y dy. 2x is over here, and then I would just multiply the dx over to the other side. So that's how we're able to keep this as a product of an expression or function of y with dy, function of x times dx. So that's a proper form for integrating. So then at this point, you just integrate each side of the equation. So y would become 1/2 y squared. This side here would become 1/2 x squared. The 1/2 and the 2 end up canceling out, so I'm going to erase that there, and then plus c. So I know that when we take the antiderivative, we technically have a constant on each side of the equation, but rather than writing a plus c on each side and accidentally canceling them out, we say that we know that there's going to be a constant, we're just going to keep it on this side. So you only have to write the plus c once for this. All right, so let's go ahead and look at some different examples and look at some different vocabulary and wording that'll be helpful as you're solving these. So if it says find the general solution to y equals f of x, just to note that what this means right here is this implies that you do need to solve your final answer for y equals, so that's important, because sometimes you won't need to, but most of the time you will. So we want to find the general solution to this differential equation. So I see dy dx is equal to y plus 5. So taking a look at this and for separating variables, I see that there aren't any x's. So I need to keep y on this side since I have dy on top. So what I'm going to need to do with this, notice it's in parentheses, that might be helpful for seeing what to do with it. If I want to divide both sides to move this over to the other side, I need to take the whole thing over there. And then I multiply this side here by dx. And what was left over here was an implied 1. The reason I have to take the whole y plus 5 over is I can't subtract y from both sides because then that wouldn't be a product or a quotient with dy. So that's why I have to take that over all as one piece, because dy minus y would not be a proper form for integrating. All right, so if we go ahead and integrate this, it's technically a small u sub. Your u is y plus 5. The derivative of that is just 1 dy, so you don't have to worry about any chain rules. So this is a 1 over u problem. A lot of you are to the point where you might not even need to write out that substitution anymore. I just want to make a note of it so you can see where I got my answer from. So this side here is going to integrate to natural log of the absolute value of y plus 5. 1, and it turns into x, and then I have plus c. So I need to solve this for y equals, so I need to get rid of the natural log. There's two different ways you can think about this. The inverse operation to natural log is to raise each side, or as an exponent to e, because these being inverse operations, they cancel out. Another way to think of this is to switch from logarithmic form to exponential form. So this is a base e, so we could think of it as e to this power is equal to y plus 5. So whichever way of thinking is easiest for you, I guess I'll probably think of it more as inverse operations, but both ways are equivalent ways of thinking. So we want to talk a little bit about some simplification here. This is a common technique that's used in this lesson, and we'll review it again, but the plus c isn't real easy to solve for when it's up in the exponent. So I'm just going to explain how they treat that over here. Remember when we add exponents, that was the same as a product. So that would be the same as like e to the x times e to the c. Well, this is still some constant. So throughout this lesson, as an easier way to find c in problems where we need to find it, instead of writing it the plus c up in the numerator, they say if I have e to the x plus c, I'm able to call that some constant times e to the x. So I know that it's not the same c as right here, but it's still just a constant. So we're going to treat e to the x plus c as c e to the x. So when I solve for y equals, I subtract over the 5, and then I have plus c e to the x as my final answer. All right, so let's solve another differential equation. So this one has a y prime in it. If it helps you at all to write out the dy dx for separating, you might want to do that. You'll commonly see it written both ways. So the first thing I want to do, since I want to work with products rather than any sums or differences, is that I'm going to bring that to the other side. So this is still over here, and then subtract over the 2, or add over, pardon me, the 2xy. All right, so when I separate, again, I want to keep y on this side. So I'm going to keep y over here. I would have to divide by y on this side. Okay. The x's will stay over here, and then I would have to divide by this whole quantity over here. Oops, 1 plus x squared. Dx. All right, so now I have it in a proper form that it's some type of a product or quotient with dy or dx on both sides. So I go ahead and integrate each side. So this is natural log of y. This is a small u sub here, so with your u being 1 plus x squared, the derivative of that being 2x dx, I have the 2x, so that's good. So this is a 1 over u du as well. So this side will be natural log of u, so 1 plus x squared plus c. All right, and so again it says to solve. It didn't say to solve for y equals f of x, but I am going to solve for y equals, because if you can, that's probably going to be the most useful type of solution to you. So I go ahead and I going to do base e to both sides. So then that's going to cancel, leaving me with y equals. The plus c in the numerator is going to come out front as a constant. The e and the natural log are going to cancel. So then it would just become c times 1 plus x squared. You can leave the absolute value. It could also be simplified out since any number squared is positive plus 1 is positive. So you don't need the absolute value there. So that would be the general solution to that differential equation. All right, so this is a certain situation that has many applications in differential equations. So this is the type of scenario that we're looking at. It's one where the rate of change of a variable with respect to time is proportional to this variable. So we want to get this statement written into an equation. So let's just pick something for the variable. You don't even need to be creative. We could even just say v for variable. So the rate of change of this variable with respect to time. So remember, rate of change is a derivative. So the rate of change of some variable v with respect to time, so dv dt, is proportional to this variable. So that would mean that it's equal to some product with a constant. So I'm using k as a constant. All right, so what would be the solution to this differential equation? So I go ahead and I want to separate my variables. So I need v on this side, so I divide by v. I'm just going to leave the constant over here with dt. Okay, so I go ahead and solve. So natural log, absolute value of v, this would integrate to kt plus c. If I want to solve for v equals, I do base e to both sides. So just again as a quick reminder that even though that this plus c is up in the exponent, that this constant can be brought down like that. So this is in the form v equals c e to the kt. So although this form might be something that doesn't maybe seem familiar to you, this is actually very similar to the PERT equation that you use starting in Algebra 2. So it looks a lot like that. All right, so let's go ahead and maybe find a little more information. All right, so let's go ahead and start with writing the differential equation. So the rate of change of y, so either dy dt or y prime, is proportional to y, so equals ky. And we know that when t equals 0, y equals 2. When t equals 2, y equals 4 as well. So what's the value of y when t equals 3? Well, if they want to know about the value of y, that means we need to solve this differential equation. We just talked about how when the rate of change of a variable is proportional to that variable, that we're going to be working with this formula, y equals c times e to the kt. You're always welcome to solve this differential equation if you forget this fact, but then you're also welcome to jump to this shortcut as well. So either which way you want to do that is fine. So we want to go ahead and use the information that we have up here to find c and k. So notice that there's two unknowns here. That's why they had to give us two pieces of information. So if we go ahead and plug in one of them, I'm going to use the one with 0 because often that allows you to simplify a little bit quicker. So plug in 2 for y and 0 for t. So I end up getting e to the 0, which is 1. So I end up getting c to be 2. Often c will be your initial condition because of this fact. So now I have a little bit more information. So y equals 2 e to the kt. So now I just need to find k. So I go and plug in when t is 2, y is 4. Okay, and I want to solve for k. So if I'm solving for k, I need to isolate e. So I divide both sides by 2. Okay, to get k out of that numerator, I need to natural log both sides. So natural log of 2. When I natural log e, it cancels. So I end up with 2k. All right, so then k is going to equal natural log of 2 divided by 2. I would recommend when you're using this to either use the exact value in your calculations or to store the variable in your calculator. So what I mean by that is when you're in your calculator, you can do the natural log of 2 divided by 2. And then if you're choosing to work with this as a decimal, you need to go 4 or 5 decimal places to stay accurate to 3 at the end. But I would strongly recommend, since this is always a calculator application, to go ahead and store this as k. So I hit the store button, and you can even call it k, so alpha k. Then you can just recall that variable or constant as you're working. So what I mean by that is it says, what's the value of y when t is 3? So what's y? So 2e to the k times 3. So I know k is this value, but when I am storing it in my calculator, I'm just going to recall k. So let's go ahead and see what I mean by that. So you can go 2e to the alpha k times 3. So then what that did was it allowed me to just recall that value that I stored as k. So it's a really useful way to be able to ensure your accuracy to at least 3 decimal places. So I would strongly recommend that you use this calculator application to be able to come up with the correct answer. So then I would say that y is equal to 5.656 chopped to 3 decimal places. All right, so let's try to formalize this. So any differential equation that follows the form that the rate of change of the variable is directly proportional to the variable is actually considered a case of the law of exponential growth or decay. So one of the reasons that we're allowed to make the shortcut is someone has proved that this will always be true. So it's a law or a theorem. So if, for instance, if we say that this variable is y, the rate of change of y with respect to time is proportional to y, so then we know y is equal to c e to the kt. And again, just as a quick reminder that this greatly resembles the PERT equation that you were using in Algebra 2. Okay, so let's go ahead and try an application of this, one of the most common being radioactive half-life. So suppose a 10-gram sample of plutonium has a half-life of 24,100 years. So if you have 10 grams, that means at time 0 you have 10 grams. Half-life would mean that it takes 24,100 years to decay to half. So after 24,100 years have elapsed, I know that I would only have 5 grams. How long does it take the sample to decay to 1 gram? So you can go ahead and we're using the law of exponential growth or decay, so y equals c e to the kt. You can go ahead and plug this in, but you can also know that since 10 is the initial condition, that can be substituted in for c. All right, so then I need to use this information here to find k. So 5 is equal to 10 e to the k times 24,100. So if I want to solve for k, I need to divide by 10. So 5 divided by 10 is 1/2. And then I would natural log both sides, so natural log of 1/2. And then to get k by itself, I would divide by 24,100. I want to go ahead and store that value as k in my calculator for future calculations. So natural log of 1/2 divided by 24,100. And I want to store that. I'm just going to call it k since that's what I did in my equation. That seems the easiest to follow. All right, so then now I'm able to recall that as my value of k when I have other questions to answer. So the question was, how long will it take the sample to decay to 1 gram? So 1 is going to be my y. So 10 is still my c value. I have a value for k and I'm solving for time. So I go ahead, if I want to solve for t, I need to divide both sides by 10. So I get 1/10 e to the kt. To get t out of the exponent, I want to take the natural log of both sides. And then to isolate t, I would divide by k. So on my calculator, I want to take the natural log of 1/10 and divide by k. So natural log of 1/10 divided by k. All right, so then that is going to take a picture of that so I'm not flipping back and forth. Move that down here. All right, so then I know that the amount of time that it's going to take is 80,058.467 years. So a lot of the applications that you have using exponential growth and decay will be similar to that. I want to look at one last example that just starts with a different piece of information just so you algebraically know how to treat that. So suppose an experimental population of fruit flies increases according to the law of exponential growth. So we're working with y equals c e to the kt. There are 100 fruit flies after the second day of the experiment. So after 2 days have elapsed, there's 100, and 300 after the fourth day. The reason I want to talk about this is just because algebraically, how do you get the c in the k? Just because it's a little bit different than the last one. So, and the question they want me to ask is approximately how many flies were there in the original population. All right, so it doesn't matter which one of these I start with first. So if I go ahead and plug in 100 here for y, and 2 and for time, I want to go ahead and I want to solve for one of these variables. Since I don't have a 0 in there, this is just a little bit harder to work with. The easiest variable to solve for, or unknown, would be c. So if I go ahead and solve for c, I'm going to have 100 divided by e to the k times 2, or 2k. Well, as it stands, it's not particularly helpful, so let's go ahead and plug in the other point. So 300 equals c e to the k times 4. All right, so then I go ahead and what I did in the last problem was now I have something that I can substitute in for c. So I have 300 equals 100 divided by 2k times e to the 4k. All right, so this actually simplifies pretty easily. So I'm going to leave the 100 here for right now. If I have e to the 4k divided by e to the 2k and I subtract exponents, 4k minus 2k is 2k. Now to solve for k, I just divide both sides by 100, so 300 divided by 100 is 3. Then to get k by itself, I would need to natural log both sides and divide by 2. So that's what k is equal to. All right, so it asks for how many fruit flies are in the original population. I have an equation over here that says c is equal to 100 divided by e to the 2k. Well, now I know what k stands for. I'm going to go ahead and do this on my calculator. So k was the natural log of 3 divided by 2. I'm going to store that as k. All right, and then c is equal to 100 divided by e to the 2k. All right, so my original population is 33 and a third, it looks like. Since I would accept going to either 3 decimal places because that's what AP rounding goes to, or if it makes more sense in this context, since it said approximately, because we're not going to have a third of a fruit fly, we would say, approximately 33 fruit flies. I know that this example wasn't much different than the last one, but I just wanted to make sure that you knew how to deal with, if you weren't given the initial condition, how you can find the c using this substitution technique. So in this lesson, we talked about how to separate variables to getting the y's on one side and the x's on the other, and then taking the antiderivative of each side. And then a commonly used application of differential equations, the law of exponential growth and decay.